Hello. These are the Exam 3 review slides for the for spring 2020. So these are a little bit different than the ones we've done before, where I'm just going to walk through the slides because of the craziness of this spring, and just tell you, what sorts of questions are going to be important as far as with the multiple choice questions. So as you're going through these slides, what you're going to look for are things that are written in purple. So that means that it's going to be important. So for these, so like for these types of reactions, right? You're gonna what you're looking for is let's see the annotation on. It's this right here, right? So you're gonna need to know, if I should, if you get a question about the reaction, if you have two substrates, right? Are you going to tell it's a substitution, elimination, or addition or rearrangement? So with substitution, right, you are swapping parts of the molecule, right? So you're in this case, right, you're swapping this this OH gets put on the molecule, and then the bromine here goes away. So you're swapping parts. With elimination, you almost always end up making a you eliminate part of the you break off part of the molecule, and usually you leave a double bond behind. So in this case, you're eliminating HBr from the molecule and leaving behind the carbon-carbon double bond. Okay, for addition, you have two molecules, and they're coming together to make one. So here it's the opposite of the elimination. So in this case, right, we're adding an HBr molecule onto this ethylene molecule. With the rearrangement, the atoms are basically rearranged in space, and so you could have a rearrangement where the methyl group, say, goes down here. But in this case, you've got the you have things where it goes from cis to trans, and it's the molecule itself. The atoms are still are still contained within the molecule. They're just arranged slightly differently. With that, so you want to know if you get a question about what type of reaction this is, being able to identify the four different types. So you are going to want to know. So down here, right? How the electrons go. If you have a heterolytic cleavage, that basically means you've got your two electrons here, and both of them go on to one side. Okay, so that's indicated by the double barbed arrow here. It's a full arrow. That means both electrons are going over here, and so these two electrons turn into this new set of lone pairs. Okay, so if that happens, right, so these electrons go over there, that's indicated by the full arrow. Now, if you have homolytic cleavage, right, now you've got the two electrons of the double bond, or of the bond. Now what you're doing is you're saying one of these is going onto the carbon, and one of them is going on to this group here, and so that's these individual electrons here. So indicate that you're only doing one, moving one electron over, right? You are, it's just a single barbed arrow. Okay. Now, to know, so know the difference between a nucleophile and electrophile. So nucleophile, it has a lone pair. It has to, because what it wants to do is it wants to make a new bond, and so it's going to have negative character to it. So that either negative charge or it's going to be at least be part of a polar covalent bond where it's the negative part. And what's going to happen is so it's the nucleophile takes its one of its lone pairs, doesn't matter which one you pick, and it's going to make a bond to the electrophile, the thing with the positive charge, positive character. And notice how it's a full arrow, so that means both electrons are going, and so this lone pair becomes this new bond here, okay, and that's what indicates this. So the thing that does the attacking is the nucleophile. The thing that accepts the electrons, that's the electrophile. Now you can do this if both of them have an unpaired electron, right? So that you can have both of them contribute one electron, and so this one and this one come together to make this new bond here. So this is a radical reaction where you take one electron from each atom, you bring them together, you make yourself a new bond. Now again, you just need to know the difference between nucleophile and electrophile. Nucleophile is the one it needs to have a lone pair because it wants to attack something that has positive character to it. So in this case, it would be the thing that it has the positive side of a polar covalent bond. Okay, so this negative is attracted to that partial positive, so it wants to make a bond to it. The carbon can't have 4 bonds, so it has to push these electrons up here. Okay? So these electrons here become this new bond here. Okay? And then these 2 electrons here, right, from that bond, become this new set of lone pairs there. Okay? So that's where you keep track of these. Okay? The electrophile is just simply the thing that takes the lone pair from the nucleophile. Now, as far as thermodynamics go, so what you need to know is it's spontaneous versus non-spontaneous. So this would be, you could also think of exothermic, exothermic versus endothermic. Meaning spontaneously, right? So it drops in energy, it releases the energy, or you could do non-spontaneous, where it has to go up into energy. Now, if you're looking at the equilibrium, right? So if you're at equilibrium, right? Equilibrium would equal 1, right? So remember, it's products over reactants, right? And you're not going to have to do any actual calculation, okay? But if you have a big number of products, a big numerator, a small denominator, right? That means that so this is KEQ. That means that the equilibrium constant is going to be big. It's going to be larger than 1. So if this was 10 and that's 1, right? So that the equilibrium constant is going to be 10. If instead it goes towards the reverse reaction, the reaction favors the reactants, then you would have, say, 1 here and then 10 down here, so it'd be 0.1, so it'd be less than 1. So you can always think of it that way, but just being able to recognize it. Okay? So you're going to want to know the different parts of an energy diagram. So to know that, say, the activation energy is from where the reactants start to the highest transition state, so to the highest hill. That energy gap, that's the activation energy. Okay. Also, you want to know. Let's see, this might be later. Okay. So whether it's fast or slow is only determined by the activation energy. If it's a small hill, we can go over fast. Is reaction favored, or is reaction or the products of the reactants favored? That has to do with which side is the lower side. This is the reactants, that's the products. And so in this case, in both of these cases, the products are favored because they're lower energy. In both of these, the reactants are favored, okay, because they're lower energy. These two are going to be fast to get to because the activation energy is small, because the hill is very small. Here the hill is very tall, so that means it's going to be slow. So just sort of in general sort of terms, which you'll need to be able to recognize. Okay. So for intermediates, right? So the intermediate is going to be right here. It's this dip in the reaction coordinate. So you have so that each one of these peaks is a transition state, and between the transition states you're going to get an intermediate. Now you can't isolate it, but you can detect it. And so you can have more than one. You can have several intermediates. You can have several transition states. But the activation energy is going to be the one between here and whatever the highest hill is here. It could be the first one, it could be the second one, it could be the third one. It doesn't matter. Right? So that if this hill went way up there, then it would be the transitions activation energy would be way up here between these two. stuff like that. But know the difference between intermediates, transition states, and be able to figure out which, which peak is going to be the activation energy. Okay? So you can't have multiple, you can have multiple transition states. You can have multiple intermediates. Here there's only one intermediate, but there's two transition states. So this is these high energy sort of high energy states of the reaction where you're breaking bonds, stuff like that, and then you come down here to a slightly more stable version, and then you break another bond, and then you form new ones, and then you're done. Okay, so kinetic versus thermodynamic control. It all has to do with if I were to give you a reaction, right? Give you these this product distribution, you could tell which one's the kinetic product and which one's the thermodynamic product. The kinetic product is formed at low temperatures. Look at that. Okay. At high temperatures, the thermodynamic product is formed. Okay, so if you see it, it's at the lower temperature, this is formed, this one as opposed to this one, then this would be the kinetic product. This one is formed primarily at higher temperatures, and so that must mean it's the thermodynamic product. So now for catalysts, what you need to know is that they don't deal anything with delta. This is always the same. Okay, this does not change. That gap. What changes is the activation energy. Okay, the path that it goes from here to here is different. Okay, instead of having to go through this really high hill, you bore right through it, and that's it. All it does is it speeds up the reaction. It doesn't deal anything with the overall thermodynamics of the reaction. It's only dealing with this activation energy. That's it. It just speeds it up. The enzymes, okay, those are actually no different than any other catalyst. So that's all you need to know. They're just biological catalysts, but they just speed up the reaction by lowering the activation energy. Okay. So it would probably be a good idea to know these, be able to know the nucleophilic attack up here. So this can't have 5 bonds, so you got to push these away. While here, again, this is a nucleophilic attack, but you're making a 4th bond, so you don't have to move anything around. For here, right, you have, as this attacks, these have to get pushed away. So you make this product. You're not going to get a situation where you have 5 bonds under that carbon. Okay, it happens all in one step. This comes in, that gets pushed up. Okay, because you cannot violate the octet rule. You can sometimes have the electrons, the leaving group, okay, just leave, and what's going on here, right, these 2 electrons from the bond, both of those, right, it's a double-headed arrow, so both of those go up to make a new bond here. But again, remember there was only 3 bonds shown, so there's a hydrogen here, so that carbon only has 3 bonds, so now it's got a plus charge. Okay, you can have lone pairs come in and grab grab hydrogens, right? Because remember, this is a partial positive, partial negative. It is a polar covalent bond, even though there's a positive charge here. There is this is a polar covalent bond. Same thing here. Partial positive, partial negative. Oops, partial negative, partial positive. Sorry. So it's going to grab that hydrogen. But hydrogen only needs 1 bond, so these electrons have to go somewhere, right? And so, oops, let me do this in red. Right? So these electrons here get pushed onto the oxygen to make this new set of lone pairs. Okay, because hydrogen only needs the 1 bond. Now, moving on, Bronstead-Lowry. So the Bronstead-Lowry definition is that it's all about protons, right? So it's all about hydrogens moving around. Most of the time we're going to be dealing with Bronstead acids and bases, unless you specifically ask about Lewis acids with bases. Okay, but there's actually not that much difference between them. So the acid donates the hydrogen. Okay, the base accepts it. So in this case, right, what you're doing is you're taking this lone pair, you're grabbing that hydrogen, pushing those electrons on there. So when you go from here, when you look from here to here, right, this molecule has grabbed the hydrogen. So therefore, this must be a base. Okay, this HCl has lost a hydrogen, and so when you compare this to this, and so it has, it's serving as the acid. Now, these are the products. Now, if you were to run the reaction in reverse, okay, if you run it this way, okay, now this is coming in and grabbing it, and so in this case, this is acting like a base, and then this is acting like the acid. So, if you're an acid on this side, okay, the corresponding product is going to be the conjugate base. If you're a base on this side, the corresponding molecule on the other side is going to be the conjugate acid. Okay, so know how to do that. You know, it's kind of wrap your brain around it, but you got to deal with it. Okay. Okay, so for Lewis acids, okay, Gilbert Lewis went in and expanded the definition of what an acid and base is. It's all it's saying is that acids will accept a lone pair, just like hydrogens, just like H+, right? It accepts that, it wants to have a hydrogen grab, hydrogen wants those lone pairs, okay? And the bases, it just has the lone pairs to give, okay? And so for here, you've got the iron, it's a +3, right? So this has a lone pair, right? And so it makes a it makes a bond here, and so, but it's no different than H and OH. Okay, so just like ammonia, right? So, but that it has its lone pairs, it attacks the hydrogen. These electrons get moved over here. So now, this is the Lewis acid right here, right? It's grabbing the hydrogen, or it's accepting these lone pair to make a new bond. These so it has and so you kick this away. So the acid in this, the proton here is acting like a Lewis acid. This is acting like a Lewis base. No different than if you're at aluminum chloride, right? So with that, so it is accepting these lone pairs. So again, this is the Lewis acid, or Lewis base. This is the Lewis acid. So it's no different. So Bronstead-Lowry is just a subset of Lewis acids. It's just specifically talking about H pluses moving around. Okay, so we talked about hydrolysis, carbocations, things like that. We talked about this before. Okay, so what you need to know for this, you do not need to know these numbers. Okay, you don't need to know the pKa numbers, but what you need to know is the trends, right? So that as the number gets smaller, okay, the acid gets stronger. Okay, but if you have a strong acid, its corresponding conjugate base is going to be very, very weak. Okay. Conversely, if you have something like water is a pretty crummy acid, right? Stuff like that. And so but the corresponding conjugate base, where you've ripped off one of the hydrogens, right? You make hydroxide. It's a really strong base. Stuff like that. And so there's this, strong acid makes weak conjugate bases. Weak acids make strong conjugate bases, stuff like that. And so we can use those trends to determine acidity. So if you have, right? So if you have this base here, well, is it a strong base? Well, look at its regular acid form, HCl. Well, HCl is a strong acid, right? So that must mean this Cl minus is a weak base. Here you've got this one. Well, this is acetic acid. This is vinegar, right? It's got a fairly low pKa. So this must be a fairly. It's not as bad as this one, but it's still a fairly crummy base. But if you have hydroxide, right? Well, if you look at the water, right, its pKa is pretty high, and so that must mean this is really strong. So you can use the pKa table to predict what its base form would be like, how strong it would be. So when you're trying to predict the reaction, what you want to do is you want to look at the acid on this, the pKa of the acid on the reactant side, and the conjugate acid on the base side. Okay, and so you can look at this and so you're going from 4.76 to almost 16. You go almost from 5 almost to 16. You want the number to go up. Okay, and so that means this reaction is going to want to go this way. That means it's going to want to go this way. Again, if you can't remember it, always think about this HCl plus OH minus going to HOH plus Cl minus, right? So HCl, right, this pKa, right, is about what, -7? This one is about 16, right? We know this reaction is going to go, so that must mean the trend has to go towards the higher, the reaction wants to go towards the higher pKa. So again, whenever you're thinking about acid-base reaction, if you think about this reaction, everybody else works exactly the same way. Okay, so if you have this, right, you're going from 25 to 35, that means you're going up in pKa, so that means the reaction must be going that way. Again, for here, 2 to 4, right, it's going to go towards the higher number, so the reaction must go this way. For 12 to 10, well, the reaction is going to actually want to go this way, right? By that towards the higher number, so it must be this reaction here is this product here is the favorite one. Have the reaction go in reverse. Now, in order to make a molecule more soluble, okay, you can give it a charge. If it has a carboxylic acid or something like that, something acidic, you can put in base, give it a negative charge. The other thing you could do is if it has amines in it, you could add HCl, get a little bit of acid to give it a positive charge. That's what makes, this is a very common strategy. So if you have a molecule, you want to make it more water soluble, you give it a charge. Okay. Now, next up, we're going to be talking about, so the acidity. Okay. Now, there's a couple of different, things you have to look at with here. So the first one is, if you're looking at the bond that's the atom that is attached to that acidic hydrogen, okay, the bigger the bond, okay, the bigger that atom is, the more acidic it is. Okay, just because it's not holding on to that molecule nearly as tightly as if it as the radius of that increases, the less it's able to hold on to, the weaker this it's able to hold on to the hydrogen. Now, the electronegativity also does play a role, okay, and so the more electronegative it is, the weaker this bond is, or excuse me, the weaker this bond is going to be. So the trend is, if you're looking at the atom that is closest to the that is holding directly onto that hydrogen, the closer it is down to iodine, the more acidic it is. And so when you're going across, you increase acidity. When you go down, you increase acidity. Okay, so it's same trend holds here in this column here: oxygen, sulfur, selenium. Right, you become increasingly acidic. Okay. Now, for hybridization, this is one of those things where it really only comes into play with the with carbon atoms, and it turns out if you have an sp carbon, that's so this is sp, right? This is sp2. This is sp3. So it turns out that the CH bond where the carbon is an sp is much more acidic than if it's an sp2, which is more acidic than if it's an sp3. So with that, so you just need to know the trend. Okay. Now, next up are inductive effects, and so this is having electronegative atoms near that bond, near that acidic hydrogen. Okay, so if you were to say, if you were to take acetic acid, so remember this is a carboxylic acid. So with that, so if you have just regular, CH bonds near it, right, pH is about 5. But if you put a single fluorine on there, it dramatically drops the pH right down to 2.6. Now this is not on the the hydrogen, right? This is an OH bond that we're talking about. But having electronegative atoms near it makes a big difference. So for that, and the more electronegative it is, the more acidic it is. So if you have chlorine near it, it's not going to be quite as acidic as if you have a fluorine near it. Okay, but you're saying, hold on, wait. You said that being closer to iodine makes it more acidic. No. That's only dealing with the atom that is holding the hydrogen. After that, then it's just straight electronegativity. After that, okay. The more of these you have, the more electronegative atoms you have, the more acidic it is. Okay, so monofluoroacetic acid is 2.6, trifluoroacetic acid is -0.3. Okay, but they do have to, in proximity does make a difference, right? So as the electronegative atom moves away, the acidity, these inductive effects start to dissipate. So the other thing we can have is we can also have particularly a C double bond O next to an acidic bond. It's going to make it more acidic. And so if you look at acetic acid compared to ethanol, okay, there's a couple of different things happening. One, you've got a very electronegative atom in oxygen right next to it. But you also have this resonance effect where if you remove the hydrogen, you're going to be left with the carboxylate with a negative charge here on this oxygen. That negative charge can be borne by more than, by both of these hydrogens, or excuse me, both of these oxygens. If this same thing happens with the ethanol, all of that negative charge is only on that only on the single oxygen. Usually, after if you remove a hydrogen for this, the more generally, if you can make resonance structures, the more acidic the molecule is, because the molecule itself is able to compensate. So it's not as big of a deal to the molecule. Again, with the C double bond O, you also have a very electronegative oxygen here. So again, you've got these inductive effects, which are literally pulling the electrons towards the oxygen. So less fewer electron, less electron density between this. The OH bonds means that there's just not as much glue holding this OH bond together. Okay, so having these, having the resonance stabilization, so particularly having a pi bond directly adjacent to that, like this here, the OH bond, makes it, again, you're going to have this resonance stabilization. And so if you remove this, you have all sorts of resonance structures, all, 3 of these carbons as well as the oxygen can bear that negative charge. You don't have that option with the cyclohexanol, and so everything is going to be borne by that oxygen. Okay, so you need to know. So this is the process you need to follow. Okay, to be able to, if you have 2 molecules, being able to do this. So if you follow this sort of decision tree, you'll be fine. Okay, so the first thing you're going to want to do is you're going to want to find the most acidic hydrogen, and 99 times out of 100, it's going to be the hydrogen that's not on a carbon. Okay, there's an exception to that, but for the most part, it's going to be the hydrogen that's not on a carbon. After that, okay, then you have to look at what atom it is actually holding onto that hydrogen. If it's and the closer that is to iodine, the weaker that bond is. And so if you're comparing nitrogen to oxygen, right? Oxygen is closer to iodine, so it is going to be more acidic. If you're doing oxygen versus sulfur, an SH bond is going to be more it's going to be more acidic than the OH bond. Okay, if this is a tie, then you come down and you say, okay, is there a pi bond? Is there a double bond immediately adjacent to it? Right? It can be a carbon-carbon double bond, it can be a carbon-oxygen double bond, it can be a sulfur-oxygen bond, whatever. Is there some sort of pi bond next to it, immediately adjacent to it? If there is, then it's going to be the more acidic of the 2. Okay? If they both have pi bonds, then you come down and you look at electronegative atoms. So this is where the fluorine comes into play. So the more, the closer something is to fluorine, the more electronegative it is. Okay, and so if you were to look at, so let's say you had OH versus, right? So if you had this one versus, NH2. So what you would do is you would come in here and say, okay, Where's that acidic hydrogen? Well, it would be here and here. Okay, because it's the hydrogen that's not on the carbon. Okay, they're different, right? So OH versus NH. It doesn't matter which NH you're talking about. But oxygen is closer to iodine on the periodic table than nitrogen is. So that makes this one more acidic. Okay. Now another one you can look at is to say, well, that. Okay, so if you look at these two, so the most acidic hydrogen on these guys is going to be here and here, right? That's the hydrogen that's not on the carbon. Okay, so so we did this. They're both the same, OH, so that's a tie. Now, do they both have pi bonds next to it? Yep, they have pi bonds next to it. Okay, so that means they have. So they're both tie on number 3 here. Number 4 is electronegative atoms. Well, they both have an oxygen, so that's electronegative. Okay, but they also have a chlorine versus a bromine. Now, which one of these is more electronegative? You want to look at chlorine is closer on the periodic table than bromine is. So that means this is more electronegative, which means this is going to have a bigger effect on this OH. And so in this case, this one here is the more acidic. Now you're saying, wait, hold on. I thought you said something about iodine. No. That's only for step 2. When you're looking at where that acidic hydrogen is, that's the only time iodine comes into play. Okay. After that, you're just dealing with straight electronegativity. Okay. So follow these steps. Don't rush yourself. Follow this decision tree, and you'll be just fine. Okay, nitro can also work with this, and so this is something where if it's on a phenol, okay, so it's here. If you take off this OH, right? So the phenol is fairly acidic because you can you can get resonance stabilization, right? So the positive charge can go here, 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 and here. Okay, so that's pretty good. That's a lot of resonance stabilization, and the nitro groups just because it's got that positive charge right next to the ring, it makes it more it has that inductive effect, so it makes it more acidic than a regular phenol. But if it's in this para position, in the 4 position, not only do you have these regular these same effect, these same resonance structures, but also you can have, right, you've got a negative right next to the positive that's on the nitrogen, so these can come down and make another resonance structure where these collapse down to make a new bond, and then nitrogen again can only have 4 bonds. So now we're going to push these electrons up onto that oxygen, and so we can have an additional resonance structure. And so since we have an additional resonance structure, that makes it even more acidic by 10-fold. So having it, not just having the for things like nitro, not only having it on there is going to make it more acidic, but having it in the correct position so it can help out more will also make things more acidic. So nitrogen's, this one here, I'm not really going to ask you, but just as a reminder, it follows the same rules as oxygen. Okay, so talk about conformations. Okay, so with these, okay, we're going to be talking about, so if they're sort of temporary shapes that are caused by rotation, and so remember with a carbon-carbon bond, right? So with there's a single bond, you can get rotation through here, right? So if we have this, right, you can rotate this bond, no problem. Okay, so there's a couple of different ways that we can look at this. If we're going to look at the side, so you can draw it like this as sawhorse formula, and don't forget the wedge means the bond is coming out at you, and the dash means it's going away. Okay, but we can also do this and draw what's called a Newman projection. Okay, and so this is a way of if you're looking at this. Okay, so you've got the two carbons. Okay, if you were to rotate this. so that you're looking straight down this carbon-carbon bond, okay? What you'll see is this carbon is obscuring the carbon behind, so you can't see it, but you can see the things sticking out from it, okay? And so this front carbon, you can see the, these two blue balls and this, this hydrogen, this hydrogen here. You can't see the carbon, but you can see the things that are sticking out from it. And so as you rotate it, you can, you look down the bond, okay? And the way that it's represented is right here. And so if this is, let's say this is carbon 1 and that's carbon 2, right? As you draw it, right, carbon 1 is still here, but you can't see carbon 2 because it's behind, right? And so what we're doing is a circle, right, with the 3 bonds coming out of it, and then we've got the ones behind of carbon 2. So this would be carbon 1, carbon 2. Now, just understand the what a dihedral angle is. So what we're doing is we're talking about the angle between one of the things on the front carbon and one of the things in the back carbon. So this one right here, so with that, and so this would be 60 degrees here from this one to the one to the back. Now the other one you can talk about is this from here to here, right? That's 180 degrees. Okay, so that's all we're talking about. We're not talking about the ones in the front, two things on the same carbon, because that's always going to be 120 degrees basically. But we're talking about one in the front, one in the back. Okay? So if all the dihedral angles are 60 degrees, so it's in this form right here. So all of these are 60 degrees, right? All of these dihedral angles are 60 degrees. It's in what's called the staggered configuration. Okay, so everything is going to stagger all the way around. Okay. If instead what you do is you put all of the atoms right on top of each other, so the dihedral angle is 0 degrees, so they're right on top of each other. Okay, this is what's called an eclipsed. So you can't see the back one because of the front one. So this is what's called an eclipsing interaction. So these actually have 3 eclipsing interactions right there, and that's typically drawn like this. You kind of move it off to the side so you can see what the heck is going on, something like that. But this is when you see this form, it means it's eclipsing. Okay, so you need to know the difference between staggered and eclipsed. So with this, so staggered conformations, right? So there's lots of room. Everybody has their own personal space here. There's social distancing. And so this one is the lowest energy, right? You can think of it as when you go into an elevator with people you don't know, what happens? You move off to the corners and you give everybody maximum space. If, as you're rotating around, so what I'm doing is I'm rotating the back carbon around. If you rotate that 60 degrees, now they're right on top of each other, here, here, and here. And the hydrogens, even though they're small, they're large enough that they can actually they can feel each other, and that's going to disrupt the structure of this thing, and so it's going to cost you energy to get it into this form. Now you can continue to rotate to get back into the staggered form, but you have to go over. You have to pay a penalty if you want to go on this side with that. And so by rotating it, you can relieve the strain. Rotate the bond. You can relieve the strain. And get back into a staggered form. Okay. Now, if you look at butane, okay, so now it's basically what we've done is we've swapped out a hydrogen in the front and a hydrogen in the back for methyl groups. You can kind of think of it like that. And so what we're going to do is we're going to keep the one in the carbon in the back fixed and rotate this around here, here, and here. Okay. Now, if the biggest group, if the 2 big groups that are hanging off here are opposite each other, their dihedral angle is 180 degrees. That's what's called the anti-conformation. So if you have one in the front, one in the back that are non-hydrogens, getting in this form is going to be the lowest energy because you have the 2 big things farthest apart. Now if you rotate it, okay, now that goes here, this goes here, and this goes there, right? You're eclipsing. And then if you, I think I talk about this next. If you rotate it again so that this hydrogen is here, this methyl is here, and this hydrogen is down here, you have what's called a gauche interaction. And that's pretty much it's when you have 2 You have a staggered configuration. But you have the two non-hydrogen things 60 degrees from each other. Now these methyl groups are large enough that they will that they do actually feel each other. And so this right here, this is what's called the gauche interaction, and it's when two non-hydrogens are 60 degrees. And so here they're starting to feel each other, and then here when they're eclipsing, oh my goodness, this is, you have the two largest groups right on eclipsing each other. This is going to be maximum destabilization. You rotate it around, right? Again, you're going to have a gauche interaction here as it rotates around, and then you're going to go to eclipsing, and then rotate another 60 degrees, and then you get back here. Now, if you were to calculate this, okay, so what you need to know is you need to be able to do the conformations. If you were to calculate these, so like that, so you could use this and say, okay, well, this is an eclipsing, and so this one is 6, this one is also 6, and this one is, I think, 4. Yes, so you could do that. What you want to do to find the most stable one is you want to get as many or as few gauche interactions as possible. Okay, so you need to go through each one of these, because if you can say which one of these is more stable, it's always going to be a staggered conformation. But you're going to say here, this is the anti, right? So that's going to be the most stable. But here you've got one gauche interaction here, one gauche interaction here, and then we're back to anti, because there aren't any, right? So this version here has no gauche interaction, while those have, each of these has one. So this is the most stable form. Now, what you need to know is to know the trend of, cyclopropane is a lot more, there's a lot of strain in here. There's a high energy, not very stable, compared to the most stable, which is the cyclohexane. So know the trend as we're going down. You don't need to know the numbers, you just need to know the trend goes down, like this. It's you increasing stability as you go from 3 to 6 membered ring. Okay. Now you need to know about the chair conformation, right? So we've got the it's kinked like this, right? So it forms this structure so that everything, so you have staggered conformations for everything, for all of the bonds. Okay, so there's no torsional or angle strains. Everything's in staggered form. This is how it's going to want to be. Okay, 5-membered rings can also kind of adapt this, a very similar structure. It's called an envelope structure, but again, we're not going to really talk about that. Now we are going to talk about these chair flips. Okay. Now, you do need to be able to determine not only the axial and equatorial, but also up and down. Okay, so axial is always either going to be straight up or straight down, and you can determine which way it needs to go by how these carbon atoms are pointing. So if this one here, the carbon atom is pointing down, that means the axial is pointing straight down. Here, the carbon atoms are pointing up, so that means the axial is going to be pointed straight up, and you can go through all of these. The equatorial is going to be off to the side, okay, from that bond. But this guy, this axial one here is higher than the equatorial, so this is considered the up, and that's considered the down. Okay. Now for this one here, this equatorial is above the axial, so this is considered the up, and that's considered the down. So up and down, axial and equatorial are two different things. Okay, they're related, but you can have axial up, axial down. You can have equatorial up, you can have equatorial down. Okay, so you just need to be able to determine which one is which. Now, the thing is, we can do a chair, a flip. Okay, so you can do this infamous chair flip. When that happens, okay, everything that's equatorial, all the axials convert to equatorial, and vice versa. Okay, but up and down don't change. Okay, so in here the bromine, so here, right, the carbon-carbon bonds are pointed straight down, so that means this is the axial, so this is axial down. That means this is the equatorial sticking off to the sides. This is equatorial, but it's up, right, because it's still higher than that chlorine. Now when we have to do the chair flip, right, now the carbon-carbon bonds are pointed straight up, so that means the axial is straight up. So now this is axial, but it's still above that chlorine, so this is still, so that's still up. Here, again, it's just sticking off to the side, so this is equatorial, but again, it's below the bromine, so this is down. Okay, so the axial and equatorial flip, but the up and down don't after a chair flip. Now you can get partial flips. These are these boat structures, and all you need to know is that boat, twisted boat, whatever, they're except for some very weird sort of exceptions to this, the chair structure is always going to be more stable than the than a boat structure. Okay. Now, as I say, so it's always good to be able to draw one of these, right? So you can draw the middle ones. So maybe it's back to red. Okay. So if you draw your middle carbons here, right? You put one up high and one down low, right? And you can. So let me 1, 2, 3, 4, 5, 6. Okay. So if you want to do a chair flip, all you do is you grab this one and send it down there, take this one and send it up there. And so what you do is then do the chair flip. So chair flip. Right? These middle ones are going to stay the same, and now this one is down here, and this one is moved up. So connect the dots. And there you go. And so 1, 2, 3, 4, 5, 6. Now, if you have substitutions on here, okay, especially if you have monosubstitutes, so that means you have something that's on the cyclohexane that's not a hydrogen, okay, these two conformations between the chair flips are not equal, okay. So what you want to do is you want to put the big group equatorial, okay. So in this one here, right, in this chair form, right, when this is the methyl is axial, right, it's feeling these two hydrogens over here, okay. But when you put in when you do the chair flip, right, the axial now becomes equatorial, and so now you don't have that. It's not interacting really with much at all, and so it's going to spend all of its time in this form to get the big group equatorial. And you can see this. So the larger the group, the more time it wants to spend in the equatorial position, right? So as these groups get bigger, to even a big T-butyl group, right, it spends 99.98% of its time equatorial and basically no time axial. You don't need to know these numbers, but you just need to know the trend. The bigger the group, the bigger the substitution, the more it wants to have that be in the equatorial position. Now, for cis and trans, what you need to know is that cis is either they're both up or they're both down. Okay, trans isn't up and down. Now, one of the things you need to know is that, right, so a dash is equal to up, and so a wedge is equal to down. Okay, so this one's up, up, okay, because they're both wedges, and so this would be cis. Right, up, up. Here, this is down, and this is up. Okay, so one's down, one's up, so it's trans. It doesn't matter if it's axial or equatorial. That has nothing to do with it. Cis and trans is just up and down. Okay, that's all it means. It doesn't matter about axial and equatorial. You can use axial and equatorial to figure out if it's up or down, but the cis and trans only deals with up and down. Okay. Now, if you have these things, right, so for here you've got cis, both of these are cis, right, so for that, so this one's up, right, because the bonds are pointed down, so that means there's an axial hydrogen here in both of these positions. So in this case, for the cis version here, you can have, it's gonna want to be here because you have two equatorials. Here you don't have any. If instead you had the trans version, now you've got an equatorial and an axial. This is axial. If you do the chair flip, you go have one axial, one equatorial. So in both of these cases, you have one of those methyl groups be equatorial. So energetically, there's no difference between the two. So it's going to spend its time 50-50 here. Here you have two equatorial, here you don't have any. So like that, and so it's going to spend all its time in this form here because it's more stable. So if you've got these two groups, if you have if the groups are not the same, you look at the size. So here you've got a giant T-butyl group, right? Here you have a methyl group, right? So this is, instead of having, you can think of this as a methyl group, but instead of having hydrogens, it has additional methyl groups on it. So really, really big. So if you draw it out, here are the two versions of this, right? Here, this is the axial, right? Because the carbon-carbon bonds are pointed up, so that means that this is axial. This one here, again, the carbon-carbon bonds are pointed up, so this is not up, so this needs to be equatorial. When you do the chair flip, right, this automatically becomes equatorial, and this automatically becomes axial, right, because axial and equatorial flip. Here, you've got your larger group equatorial compared to the methyl, and so this is going to be the more stable of the two, because it's got the bigger group equatorial. Okay? Larger group wants to be equatorial. Now, I don't think you have to know much about these. Okay, so good luck.